Welcome to our discussion on the classification algorithms. We have studied two classification algorithms so far, the decision tree and the Bayesian classifier. We will next study the third classification algorithm called the k nearest neighbor classifier. I will explain this using my by my previous discussion on the Bayes classifier. So, let us quickly recapitulate what we did in the Bayes classifier is that we plotted the we sort of considered the posterior distribution, the given an example of certain attribute value L belongs to certain class say tuna, and for each of the classes we draw the distributions, we draw the probability distributions. And for a new point L, new whose length is L, what we did was we just considered the values of each of these distributions in this posterior probabilities. Whichever distribution gave the highest value, we put it into that class. And we showed actually that theoretically, if we perfectly know these distributions, this would give the minimum error classifier. But also we observed that what happens in practice is that because of the finite sample size, we do not have infinite number of training sets, we cannot exactly know or estimate the distributions. We have some error in estimation, we actually do not know the distributions. Okay. And there are several techniques, we assume them to be Gaussian, then we find out that the boundaries are linear or parabolic, then we assume that there is a independence between the defined attributes, and we use the naive Bayes. So, these techniques of assuming Gaussian and then find from its parameter finding the decision boundary, these techniques are called parametric estimation techniques. They from the data they find out the value of some parameters. Okay. So, one critical thing about this parametrics is that you need to assume say some property of the this posterior distribution, say it is Gaussian or it has diagonal covariance matrix, things like this. We need to make assumptions, whereas the actual data might not, or in the naive Bayes independence assumption, actual data might not follow these assumptions. So, there is an alternate approach which often people make is known as the non-parametric approach. Non-parametric. So, where we will soon see, not this example, we will soon see that we need not make any such assumptions. We need not estimate some of parameters of under this assumption, and we use only the data, nothing but the data to come up with the classification. So, let me explain how to do that. So, what I do is the following. I suppose a fish of length L is what I want to find out the class of. I want to know a new fish of length L, which class it belongs to. What I do is that I make a small window of say L minus delta to L plus delta, plus minus delta, small 2 delta width window I consider around L. Okay. So, that means for example, if my L is say 2 feet long fish and delta is say 0.1 feet, I consider the interval of 1.90 to 2.10 feet. This interval I consider. Okay. What I actually want to find out is that what is the class of a fish of length L? 2 feet. Okay. So, now what I do is that how many of the Hilsa fish have a length in this lying in this interval. Okay. So, in my training set, what is the count of fish having length between 1.9 to 2.10 feet. Let me call that count as say N H. Okay. Note one thing, that this is nothing but originally when we draw these curves, we considered histograms, which are basically a series of bins where we find the count of number of points in each bin, and so the distribution was actually a collection of small histograms, bar charts. Okay. And when these bins are small enough, this would look like a, instead of a bar chart, a smooth function. So, the idea is that if I make my delta small enough, this value NH, number of Hilsa having length between L plus delta and N minus delta, that sort of is a good approximation of the probability a fish having length L belongs to class Hilsa, the posterior probability. Okay. So, think on this a little bit. So, what I do is that I count how many fish is of course, I made a small mistake, is that it is not this count, but count by total number of fish that I am considering. Okay. So, the something called a relative frequency. Relative frequency. Okay. So, what I want to say is that if my intervals are small enough, the relative frequency will give me the posterior probabilities. Okay. And so, what I do is that I repeat the same thing. So, I let me denote this relative frequency as FH. So, it is NH by N, N is the total training set size. Similarly, I compute for the tuna, I compute F tuna, and similarly, I compute F tuna is number of tuna fish having length in that interval, similarly F shark. So, 3 relative frequencies. What the base classifier what the map rule says is that you put it in the class having the highest posterior. Since my relative frequencies are a good approximator of the posterior probabilities, I can restate in an approximate form the map rule as put it in the class having the highest relative frequency. Here that would turn out to be tuna. Okay. So, note further that I can actually do one more thing. Since this denominator n is same for all these classes, I can just drop it. Sorry, I can just drop it. Still the top class would have the highest count. Okay. So, what I am basically doing is that for a piece of length L, I am taking an interval around it, and I call it a neighborhood around it, and count how many specimen in the training set have a length in that neighborhood, in that interval, and among them, suppose that length is n, so that number is n. So, basically n of the training, n number of training examples fall in L plus delta and n minus delta, and out of this n, NH are Hilsa, NT are tuna, and NS are shark. Okay. And I can sort of rewrite my map rule as check which of these counts are highest, put L into the corresponding class. Suppose NT is highest, tuna is highest, put it into class tuna, if this is highest among these three. Okay. So, I can do that. So, you note that this is for one dimension. I could have extended it to 2 or higher dimension also. Okay. How do I do that? So, let me take an example. Let me see if I have some, if I have the example already. No, I do not have. So, let me tell it like this. Suppose I have or two attributes, a length of the fish and weight of the fish. Okay. So, every face is a point in this 2 dimensional space. So, what I do, if I look at the training examples, each of the tuna, maybe they will, I am writing them as T, or maybe write them as cross. So, T I represent by a cross point, Hilsa by a circle point, and shark maybe by a dash. So, this is all my tunas. If I plot their length and weight, this is all my Hilsas. And this is all my shark. there are some small cirques, some big cirques. So, this is like this. Okay. So, when forget about what I have this duck example, I am coming to that later. So, if I have a new face, let me write it as a box. What I do, I took an interval in one dimensional case. Instead of an interval, I will take a small circle around it. It is like radius r is equivalent to the interval. I take radius r in all direction, delta delta delta, say r equal to delta r, this in all direction I draw and make a neighborhood with the point LW pair some new face that is the center. And I see among these training sets how many of them fall in this circle. Suppose n number of them fall in this circle, I count. So, this falls, this falls, this falls, this falls, this falls, maybe this falls, and see out of this n that falls, how many are tuna, how many are tuna. I just count that. NT, how many are Hilsa, how many are Sark. Whatever is the highest, I put it in that class. Okay, same principle. Same principle. So, instead of drawing this delta and all this sort of thing, deciding on some delta and all this sort of thing, because see it will depend on how much dimension you do and how do you choose a value of delta, I can sort of have an equivalent rule as follows. So, this is my attribute space or training space, sorry, feature space, and I have my training points whose class levels I know. And when a new point is to be classified, instead of drawing a delta, I sort of do a ranking. I find that among these training points, if I sort them in order of how far they are from this new point, in the order of how far they are from this new point, I sort them. So, some will be close, some will be far, I just sort them. So, it is with respect to this new point, how far these training points are. And I take among these training points the top k closest points to the new point. Which are have the shortest distance to this new point. Okay. And I call this set of points which are so this k set of, now there are k points because I am sorting them and finding the kth closest point, and draw a circle which includes this k point. Okay. So, I find the, so basically what I do, I find the kth closest point, draw a circle with this new point at center and enclosing this k closest point, smallest circle, and these k points I will call as the k neighbors of this new point, or sometimes the k nearest neighbors. K nearest neighbor, KNN. Okay. And I repeat what I did earlier, that means among this k, I find out among its neighbors how many are Hilsa, how many are tuna, and how many are shark. Okay, and whichever is the highest. So, I can alternately take it like the think of it like this, as if I am conducting an vote, an election among its neighbors, and whichever class wins the election, that means highest number of members are there from that class among these k neighbors, I classify the new point to this winner. So, take a vote among the neighbors, see how many neighbor belong to this class, how many neighbor belong to that class, and whichever class wins, put the new point whose class level I yet not know into this winner class. Okay. So, for example, here maybe the cross class is the winner, so classify this as a cross. Okay. So, this principle is called the k nearest neighbor classifier, it is a classification principle. Okay. It is not like building some tree or something. What it does is, it takes a training set, and when a new point is to be classified, it finds the distance of the new point to the training set, and sorts the distance, take the smallest k distances, and among these smallest k closest neighbor, it takes a vote. Whichever class wins the vote, put it in that class. Okay, simple. So, let me actually write down. Finds its distance to each of the training set example. So, a new point comes, that is a little bit a worrisome point. That means, when a new point comes, you have to, in order to find the k nearest neighbor, you have to find its distance to each and every training set point, each and every distance, otherwise you do not know which are the closest. Then once you compute this distance, find the k closest neighbors actually. K nearest neighbors, then find the class which has the highest number among these k examples, k neighbors. Okay, see which class has the highest. Okay, and assign that class that as the class of the. So, this is the winner class after the vote. So, the vote is just something to visualize. It actually means that basically you are finding which class among these k neighbors have the highest number of points. So, among this k, most of the points come from which class, and assign that as the class level of the new point, the class level. Okay. So, very simple rule, a little bit computationally expensive, because you have to find the distance to all these training points and you have to sort them to find out the top k, but otherwise it is a very simple rule. The good thing is that we have already shown that this is a approximation of the Bayesian classifier, a non-parametric approximation of the Bayes classifier. But this principle actually was philosophically sort of known to people before. It is like, suppose there is a new so what we have is that, let me draw this picture. So, in my training set I have different type of birds. So, this is a bird, this is a bird, if I have a bird, these are my training records, and they are described by some attributes, say the nature of their feather, their tweets, their color and so on. So, you describe them, each of the bird, by some attributes. And I have a new bird whose species I do not know. All that I do is to, in terms of the attribute for the new record, I find its distance to the known training birds. Note that training set may contain more than one duck species. There are different types of ducks. It may contain some hen species, it may contain some angry bird species. So, I find out in terms of the attribute these distances, see which is the closest, k closest, say k equal to 2 here. Okay. And among these two, in this case both are ducks, they may be if k was say 3, it may be 2 duck 1 hen. So, the majority of the members of this nearest neighbor, that class is the class of this new record, is the class of this new record. So, this is the simple rule. Okay. Now, I have this is a very popular and simple rule. There are some things we need to consider. For example, what is the value of k? How do you compute distance? How do you solve this computational time problem? And how do I construct a training set? So, these are certain issues that one needs to think of before using it as a data mining algorithm. All right. So, in our next lecture, we will discuss some of these topics. So, I hope you have got a overall idea of the basic principle of k nearest neighbor classifier and how it approximates the Bayes classifier. We will go into details of applying this for our particular problem in hand in the next lecture. Keep in mind that this is one of the most successful and popular classifier used in industry. Okay. All right. So, thank you for today. We will continue in our next lecture our discussion on this. Thank you.